Hello, everyone. Welcome back. Today, we are going to be talking about binomial theorem, which is actually our last lesson topic from all of Unit 2. So congratulations on being almost done with your second unit of the course. Okay, so let's do revisiting Pascal's triangle first, right? So let's review Pascal's triangle. We talked a bit about it last time, but today I want to actually talk about a different use for it, which is the binomial theorem. Before we get into what the binomial theorem says, we're going to talk about the Pascal's triangle. So just a reminder, Pascal's triangle looks like this. Oh, drawing it wrong. Let's see. There we go. Awesome, like that. All right, and keep in mind that the first row is the same as 0 combination 0. Then we have 1 combination 0, 1 combination 1, 2 combination O, then 2 combination 1, 2 combination 2, and so on. These are the same numbers, right? These are those same values, right? I'll do one more line. 3O. Amazing. Yes. Yes, it's amazing. Beautiful. So, next we're going to actually expand the following. Now, we already know how to expand this, right? You might be saying, well, I already know how to expand this because you've probably known since grade 10 or maybe before that. But before we get into that, I want to talk about how can we actually expand this using binomial theorem. So what is binomial theorem? Basically, it states that these are the coefficients depending on the row for each power, right? And so, for example, if we have, something to the power of 0, our coefficient is just 1, which that makes sense, right? What if our it's 2, right? We're squaring something. Then we'll use this one. We will say this is 1a squared plus 2ab plus 1b squared, right? Which, as we know, this is correct. The ones we can just take out, we can just say this is a squared plus 2ab plus b squared, like that, and be done with it. Very good. Now, what about this one here, a plus b cubed? Well, in this case, we're going to use this row over here, right? We're going to use 1a squared, or a cubed rather, and then 3 of the other combinations. So plus 3a squared b plus 3ab squared plus 1b cubed, right? So when it comes to cubing, what are our other combinations? Either we have, a to the power of 1 or 2 and b to the power of 1 or 2, right? And so we have these two as our other terms, and they must be repeated 3 times because it says so here. Now, let's say we were to expand it the other way, the way we know, we would also get the same answer, but this is a shortcut, right? This is a shorthand way that we're able to do that. Now let's talk about the general binomial theorem, right? So how would we write it out? We would say that a plus b to the power of n is equal to the combination of n comma 0 times a to the power of n plus, combination n comma 1 of a to the n minus 1. So like that next term, b to the 1, and then the next term as a coefficient times a to the n minus 2 b squared, and so on until we eventually get to, b to the power of n. So some of these can be very, very long. So far we've done ones that aren't very long, right? But that's the basic idea, is we can use these as the coefficients and then continue with those terms. And I hope that this sheds a bit more light on how come we knew to do a squared b and ab squared. Well, we had to get rid of one of the powers of a and add b in the mix, and then we had to get rid of another power of a, add another b into the mix, or I guess multiply another b into the mix, and so on, right? We have to go with with that in order to get to that binomial theorem. Now, in terms of a proof for the binomial theorem and why it is the way it is, I'm actually not going to get into that today. That's a topic for another day, perhaps. I'm just going to give it to you at face value this time, so hopefully that is all right. Yeah, I know I normally like to give an explanation for for why things are the way they are. For this one, I think we will just kind of take it at face value because that's a much more, that's a bit more of a complex topic, I feel. Okay, so let's try this one here. This one says, what is x plus y to the power of 5? Well, let's see. Based on the binomial theorem, what would that be? That would be x to the power of 5, and then plus 5 is our coefficient from our Pascal's triangle, x to the power of 4, y to the power of 1, plus what's our next coefficient? It's 10, x cubed y squared, plus 10 again, x squared y cubed, and then next coefficient is 5xy to the power of 4, and then plus y to the power of 5. There we go. All right, how about this one? 4x plus 3 to the power of 4. So with this one, we might actually need a little bit more, expansion in some ways for this one. So let's try this one. Well, here we are going to have 4x to the power of 4, first and foremost. Then we're going to have the next coefficient, so 4 times, 64 times 3x cubed, right? And then what are we going to have? We're going to have plus the next coefficient, which is 6, and then times 16 times 9x squared. Then we're going to have plus 4 times 4 times 27x. And then we're going to have plus 1 as our last coefficient times 3 to the power of 4, which is 81. And I'm actually going to simplify this further. There's clearly ways we can simplify this further and make it nicer. So let's do that. 4x to the power of 4 is 256 x to the power of 4. Then we have plus, 768 x cubed. And then we have plus 864 x squared. Then we have 432 x, and then we have 81. And this is our final answer in expanded form. All right, and let's apply it again to this even slightly more challenging example. This might look more challenging, more daunting, but what I want you to keep in mind is it's the same exact thing. We just have to think of a is equal to 3x squared, right? And b is equal to 2y. And that's all, right? And n is 5, right? So it's exactly the same thing again and again is the point I want to get across here. And so it may be harder in the sense that there's a bit more simplifying here, more terms to kind of deal with and handle. But at the end of the day, it is the exact same thing. It is the exact same thing as the earlier examples, just made a little bit more challenging by, replacing a with 3x squared and replacing b with 2y. Good. Okay, so let's run through this one. Well, what's our first thing? It's going to be, 3x squared to the power of 5, which is going to be 243 x to the power of 10, right? Because remembering our rules, our exponent laws here, right? Where x to the power of 5 times x squared is going to be, x to the power of 2 to the power of 5 gives us x to the power of 10, right? So remembering that exponent law there. Good. Then plus 5 times 81, x to the power of 8 times negative 2y, plus 10 times 27x to the power of 6, 4y to the power squared. Okay. Plus 10 again, 9x to 4, negative 8y cubed. Let's see, plus 5 times 3x squared times 16y to the power 4, plus 1 times negative 32y to the power of 5. And let's simplify that down. We're going to have 243x to the power of 10 plus, let's see, actually this will be minus 2 times 5 times 81, minus 810 x to the power of 8y, plus, let's see, 10 times 27 times 4, 1080 x to the power of 6 y squared, minus 720 looks like x to the power of 4y cubed, plus, let's see, 240 x squared y to the power of 4, minus 32 y to the power of 5. Awesome. And there we have it. We're all done. All right, well, congratulations on finishing the final topic of this unit. Best of luck on the test. The next unit is all about basic probability functions. And so I hope everyone enjoys that. I think probability is a great topic, and I promise that counting techniques will come up in this topic. I don't think the first unit will really come up much in this topic. Honestly, the first unit doesn't really tie into everything else quite as well, I would say, whereas combinations, permutations, etc., are really key to succeed in probability because they're going to help us solve probability, which you'll see later. And as is probability important to combinations, permutations, and so on as well. So it's going to be a topic that comes up again in the next unit. So do make sure you review hard for this unit, not just for this test, but also just in general, because it's key. It's going to be key, and it's going to help you succeed in future units as well. So I hope you enjoyed this unit, but if you didn't, that's okay too. And I will say this binomial theorem stuff, if this stuff specifically is stuff you didn't like, don't worry too much because binomial theorem doesn't really come up again. It's more just the other stuff in this unit that comes up again, excluding binomial theorem and Pascal's triangle. But yeah, I hope everyone enjoyed the unit, and we will see you all in Unit 3. Bye, everyone.